These liquid crystal displays, or LCDs, have become so cheap and common. It's really easy now to incorporate them into many different projects, and you can have one display for every project. Most of them come with some kind of a backlight because they're not very visible without some form of lighting from behind, and most of them are designed for that purpose. And here's an example of a backlight that I took out of another display that I managed to destroy. Oops, only half of it here. Let's get the whole thing. This is just the bezel or the diffuser. It goes over top. But it would look something like this. I took this one out of a display that I managed to destroy with environmental testing. I was freezing it and heating it to test it for a project, for a product that I was designing to go into an automobile, into heavy trucks actually, but they had to withstand quite a wide temperature range, and I managed to destroy quite a few of them testing them. But anyways, this is what a backlight typically looks like. The diffuser on the front here, I took this apart and you can see the individual LEDs. There's 30 LEDs in this one, and they're wired up in combinations of series and parallel. And what's really interesting about them is that you can see a pad here. I don't know how well this shows up in the in the screen here. You can see a pad here, one pad for each LED. The pad's actually split in the middle horizontally, and on the bottom side of the pad is where the LED is actually attached, and then there's a wire, a very fine gold wire that you can hardly see, goes from the upper pad to the top of the LED. And so these are basically what they call a chip on board. And then they're covered with some kind of a silicon material here. It's kind of rubbery. Anyways, most LED backlights that come with these liquid crystals or LCDs are designed to run off of a 5-volt power supply with a series resistor. And in my own use of these, I prefer not to run them off the 5-volt power supply because that's also supplying power to the microcontroller and all the other electronics, and I don't want to stress it any more than it has to be stressed with the additional current drawn by the backlight. You can hook them up to any voltage that you want as long as you've got the appropriate sized dropping resistor, series resistor, so that you can limit the amount of current going into the backlight, the LEDs. And you'd have to look it up for your particular LCD that you've got, what the current actually is for the backlight. Or if you have a good variable power supply, you could put a value of resistor, say 1K in series with the backlight and the power supply, and just turn up the power supply gradually from a few volts up, and just measure the current that it takes to get a good level of brightness. And it could vary from just a few milliamps to maybe 70 or 80 milliamps. I believe this one here, yeah, I wrote it on the back, it runs at 12.3 volts, 70 milliamps. For this particular product that I was designing, I got away from the 5-volt backlight, which is what the original manufacturers of these displays came with. And I worked with the manufacturer and asked them to change the orientation of the LEDs here in the backlight and make it a 12-volt backlight. So I could just hook it up to a small resistor and a 12-volt power supply, because that's what the power is in a vehicle, in a truck or a car, is 12 volts. And it just saved a lot of heat dissipation. Running them at 12 volts with a 5-volt backlight running at 12 volts would have quite a large resistor and would dissipate a lot of heat, especially with 70 milliamps being drawn into the displays here. But for my own sort of hobbyist use and other products that I've designed, I don't want to have to modify the backlight. It's expensive to do that, and I don't want to run it off 5 volts, so I want to run it off to whatever power that I'm providing to the 5-volt regulator, which could be 12 volts or 24 volts or 9 volts or something else. And it becomes a bit of a chore if you change those voltages, because you have to change the series resistor in order to keep the current in the backlight at the right level, so you don't burn out the backlights, and the LEDs are, the LEDs are bright enough that you can see it. So what I thought about doing, and what I do use now for all of my designs, is something called a constant current source. And let me explain what goes into a constant current source. Let's move all these displays out of the way, and I'll get some little schematics here going. Let's zoom in on it. So if we look at the leftmost one here, this is what you normally do. Series resistor, and there's your LEDs, and I've just drawn one in here, but there could be several in series depending on how the LEDs are arranged in the backlight. Now if this voltage here is constant, then of course the current drawn through this for a given LED is going to be constant for a given resistor as well. If this voltage varies, then of course the current is going to vary, and that was the problem that I was running into with this kind of a circuit. This is the simplest way to do it, but it has its drawbacks. Now you can add a transistor to this network here, and you bias with a fixed voltage on the base here, and it'll give you a fixed current passing through here based on the voltage across this resistor here. So you figure out what the voltage is across this resistor, and then you know that when the transistor is on, there's about 0.6 or 0.7 volts dropped across this base emitter junction. So you subtract that from the voltage across this resistor, and you get the voltage across that resistor, and of course then you can figure out the current. And this circuit will work well for many different kinds of backlights. If this voltage is constant, you can change the number of LEDs in series here and still get pretty much the same amount of current as you originally designed for in the LEDs. So I could put one LED or two or three or four in series and still have the same amount of current flowing. The transistor will automatically adjust its base emitter drop here in order to give you the right current through the LED. Now if I vary this voltage, then this current is going to vary as well, and I have the similar problem as with this circuit here. And so what you need to do is try to make this voltage here constant regardless of how much current is flowing down through this leg of the circuit. And then that leads us to this circuit here, in which I put two ordinary signal diodes, like a 1N4148, and two of them in series here with a resistor, and I size this resistor to give them a few milliamps of current, and their voltage drops, the forward voltage drops across these diodes, is going to be pretty constant over a fairly wide range of current flowing through them. So this voltage here can vary quite a bit, and the current through here will vary as well, but the voltage drop across these will remain pretty much the same. And so what happens here is we've got the same. Now the reason why I put two in here is because I use one here to cancel out the base emitter drop across this transistor, and now I've just got this one here providing a 0.6 to 0.7 volt drop across this resistor. And therefore the current that flows in this circuit, and if you remember basic transistor theory, whatever current flows in the emitter is going to pretty much the same current is going to flow in the collector. So if I got so much current here, so 10 milliamps flowing here, I'm going to have about 10 milliamps here. And so to figure out that current, you just size the value of the resistor to give you the current. So it would be the 0.6 volts across that resistor divided by the value of the resistor gives you the current flowing through it. And then again you can put in different LEDs in series here, or a different number of LEDs, or the different types of LEDs. Remember of course that the different colors of LEDs also have different voltage drops, and the white ones used in backlights tend to be quite a high voltage drop, whereas red ones produce the lowest voltage drop. But you can put more than one LED in series here and still have the same amount of current flowing through this circuit here, through the LEDs, as well as if you change this voltage here, the current coming through the LEDs here will be about the same all the time. It does vary a little bit, but it's pretty constant. So what I do when I design my circuits then is I'll put a circuit like this in here and design it for the desired amount of current, say 20 milliamps to run the backlights or whatever is needed for the particular backlight. And then it doesn't matter what voltage I apply to here, I'll still get my approximately the right current that I want. Or if I change the display that has a different kind of a backlight, that has a different number of LEDs in series here, it doesn't matter, I'll still get the same amount of current, within limitations of course. Obviously you can't have too big of a voltage here because the transistor is going to saturate, meaning there's going to be very little voltage drop between these two here, and you won't get so much voltage across here to be able to provide enough voltage to drive a large number of LEDs in series. So there are some limitations here. Of course, if you short this to ground with no LED in there, there won't be any damage done as well, because simply the current will be limited to whatever you've designed in here, 20 milliamps or whatever. The only thing you do have to watch is the dissipation in this transistor here. And basically it's just whatever voltage drop you get across the base and the emitter and the collector, multiplied by the current flowing through it, and that'll give you the amount of power dissipated by the transistor. And a fairly standard transistor in a TO92 package like this, you don't want to dissipate more than a few tens of milliwatts, otherwise it'll get too hot and burn up. So I think what I'll do next is I'll build an example of this circuit here and just demonstrate how it works. Another thought here I just had is you don't have to have just 2 diodes here. You can put more in series here. That way you can get a more reasonable value. With 0.6 volts across here, these values of these resistors gets quite small, which might be hard to obtain something that's only a few ohms. But the advantage of that, though, is that it allows a much wider range of voltages here. But if you do want to increase the voltage across that resistor to start using bigger values of resistors, then you could just put a Zener diode in here as well, of a couple of volts or whatever. But I find the simplest and the cheapest way to do it is just 2 diodes in series like this, and the values that I get here are pretty reasonable. Anyways, let's have a look at the circuit. So now I've realized this particular circuit here on the breadboard. These are the 2 diodes here. This is the resistor that supplies current to the diodes. And I chose this to be about 2k ohms, and that gives me roughly 2 milliamps at 5 volts if I put 5 volts here. And I wanted about 10 milliamps flowing through here. So I calculated that R2 here should be about 68 ohms, or 60 ohms actually. The closest preferred value I could find was 68 ohms. And calculating that out gives me about 8.5 or 8.9 volts, or current, 8.9 milliamps, or 8.5 to 8.9 milliamps in here. And when I tested it with these 3 LEDs in series, I found that there wasn't enough voltage across the LEDs to light them with 5 volts here, so I increased the voltage here to about 9 volts. And if I zoom back here, oops, wrong way, you can see the 2 meters that I've hooked up. The right hand meter here reads the voltage across the across the rail between here and here, between here and here. And this meter will read the amount of current flowing in the LEDs. And if I hook up the complete string of LEDs, ending with the green one here, you see they're all nicely lit. I don't know how well that shows up on the camera. Believe me, they are quite nicely lit. And we're reading about 9 milliamps in my circuit here. And if I were to change which LEDs that I hook up, I've got them all in series here. Oops, bumping the camera. Get it back. So if I move it over, the connection over to just having the first 2, the red and the orange, on, I'm still reading about 9 milliamps, but there's a significantly different voltage drop across here. And then I go to just 1 LED, and I'm reading still about 9 milliamps. And if I were to ground it, short it out, like that, oops, you're not going to get anything, wrong end. Go to this, I got about 9 milliamps shorted right out. Now let's hook the LEDs back up. So you notice that the voltage across the output here, across this part of the circuit, the LEDs, because I've got different LEDs in there, so it's going to be different voltages for each LED. And depending on how many I have in series, I'll have a different voltage. But you notice how the current was the same, no matter how many LEDs I had hooked up, including a short circuit. Now the other thing I can do is I'll vary the voltage here, and you'll notice that the current will change a little bit, but it's still pretty constant. Let's get over here and reach the power supply knob, and let's bring it up So you notice how the current is going up, but it's not going up anywhere near as fast as the voltage. So I've gone from, I've only increased about a milliamp, and I've gone up, well, I've doubled the voltage practically here. And then if I go back down at 5 volts, I don't know if you can see it on the camera very clearly, but down close to 5 volts, the LEDs are getting significantly dimmer. And then they go almost completely out, as you see how the current drops off suddenly. There's not enough voltage in the circuit to provide enough current to light all the LEDs at their appropriate voltages anyways. But this thing works nicely at 9 volts. And 9 volts is a fairly common supply voltage. 8 to 9 volts is a good common supply voltage to run a 5 volt regulator off of. So anyways, that was just a quick little video to show you a constant current source, which is this circuit here. Very simple, cheap circuit you can make with a few components to drive some LEDs and not have to worry too much about how many LEDs you got in series, or what kind of LED backlight you're using, or what voltage you're providing for that circuit for driving the backlights. It just makes putting a liquid crystal display, an LCD display, in your circuit with a backlight, and not have to worry too much about what voltages you're going to power it with. I find this really useful. I've got it in a number of projects now, and all I need to do is change one resistor here, and that changes the amount of current that I'm going to provide. And I just disregard the number of LEDs in series and the actual supply voltage. I just change one value of one resistor. Simple circuit to use, and works quite well, as you can see. So I hope you enjoyed the video. Stick around, I got some more coming. I got a bit of time now. I should be able to produce more videos. I've got an idea for a series of videos coming up on learning how to program outside of the Arduino world. So stay tuned. Thanks for watching. Catch you the next time.